Well, good evening, ladies and gentlemen. My name is Dave Duty. I work here on the Cassini mission, and it's my pleasure to welcome you tonight to our presentation in the von Kármán lecture series. Before I introduce tonight's speaker, let me draw your attention, though, to some exciting upcoming events in the von Kármán series. There's a flyer that we just put out on the counter. Please collect one of these. The printed brochure will be out later, but this will give you an idea of the speakers coming up in the 2008 series. In particular, next month, rather than the usual lecture here, we're going to have the premiere of a new historical video produced by Blaine Baggett, manager of the JPL Office of Communication and Education. It's entitled JPL, The Beginnings of the Space Age. This will be on Thursday, January 24th, and it will be down at Beckman Auditorium on the Caltech campus, rather than here at JPL. And then the next evening, the Friday night, the 25th, it will be repeated at the PCC forum in the usual place. Well, the California High School Cosmic Ray Observatory project, CHICOS, is a research array for the detection of ultra-high energy cosmic rays. These are single subatomic particles that slam into the Earth's atmosphere with the energy of a brick falling from a rooftop. These energetic particles produce showers of secondary particles when they collide with atomic nuclei in the upper atmosphere. In the CHICOS project, schools across the LA area provide a network of detectors to observe these secondary particle showers, and they provide a valuable population of participating teachers and students. Now, from my point of view, the Cassini spacecraft in orbit at Saturn doesn't have any cosmic ray detecting scientific instruments like the Voyager does. But everything on Cassini is controlled by a solid-state power switch that we command to turn things off and on the spacecraft. But 2 or 3 times a year, a cosmic ray from somewhere will slam into the switch and turn something off unexpectedly. Usually it's something benign, like something that's already in the off state to begin with. But last September, the last event, a cosmic ray turned off Cassini's main communications amplifier. So it gave us quite a scare. Chances are, though, it wasn't one of Dr. McKeown's ultra-high energy flying bricks. We'll give him the benefit of a doubt. His early work, tonight's speaker, got his BS in physics from Stony Brook University in 1974, and then went on to do graduate study at Princeton, earning a PhD in 1979. After a year on the research staff at Argonne National Lab, he came to Caltech as an assistant professor of physics. His early work at Caltech included searching for free quarks and neutrino oscillations. Then, during the 1990s, he focused on studying the quark structure of the nucleon. In 1999, he returned to neutrino studies with the Kamioka liquid scintillator anti-neutrino detector, or CAMLAND, experiment in Japan, which used neutrinos from nuclear power plants to demonstrate that the deficit of solar neutrinos was really due to what are called flavor oscillations of neutrinos. During 1999, he also became interested in the subject of ultra-high energy cosmic rays and developed the California High School Cosmic Ray Observatory, CHICOS, to study the phenomenon. Also, it's a novel outreach project to involve students and teachers from Los Angeles area schools in a real science project. Currently, he's developing a neutrino experiment in China to measure the last unknown angle in the neutrino mixing matrix. Ladies and gentlemen, please join me in welcoming tonight's guest, Dr. Robert McKeown.
Well, thanks very much. It's a pleasure to be here, and I'd like to thank the organizers of this lecture series for the opportunity to come here and tell you about this very interesting project, which, or rather differently from Cassini, it seems to actually turn people on. So it's, and particularly we're delighted that it turns teachers and students on to cosmic ray research. So let me begin by at least outlining the motivation for the project. Combination of doing, I'm going to find the button on here, of doing scientific research and education outreach in a rather unique way. There are these ultra-high energy cosmic rays, which I'll describe later in the talk. Questions, the scientific questions related to these cosmic rays are: where do they come from, how are they generated, and what are they composed of? At the same time, we have an education outreach component to the project in that it establishes a unique partnership between universities and high schools and also middle schools and a few elementary schools. Teachers can come to Caltech and learn about cosmic rays and particle physics. So there's professional development for teachers. We've developed school project materials in collaboration with the teachers, and we hold workshops and a summer program for teachers and students in the LA area. So the outline of what I want to talk about tonight is to give you sort of an historical introduction to cosmic rays, talk about what are these ultra-high energy cosmic rays, discuss the concept of this CHICOS project, and give you a little bit of a flavor for what the data we're getting look like and why we're excited about them, and show you the preliminary results and where we think we're going. So the first question we always get is, what are cosmic rays? And as you might imagine, if you go to your random high school or middle school, they actually have, some people have never even heard of cosmic rays, never mind know what they are. And so here's an artist's concept of cosmic rays, but of course we have something else in mind. The discovery of cosmic rays actually occurred back almost a century ago in 1911. A fellow named Victor Hess did this experiment, and people were puzzled at the time because they built the very primitive radiation detectors. They were called electroscopes, and these radiation detectors always detected radiation wherever you went, and people couldn't figure out where the radiation was coming from. The most prevalent theory was that the radiation was coming from the ground. There's radioactivity or something in the ground, but some people thought maybe they were coming from outer space. So Victor Hess came up with this idea, and I like to tell this story to students in the schools because you realize you don't have to be Einstein to come up with a really good idea in science. He came up with the idea, well, let's go take the detector up in a balloon and see if the intensity of the radiation goes up or down. If it's coming from the ground, it should go down. If it's coming from outer space, it should stay the same or go up. And he found that it dramatically went up as he went up in the balloon. Nevertheless, there were other experiments of lesser quality and so forth, and so this was controversial for quite some time. And you can see from this slide that he didn't get his Nobel Prize for this until 1936, which is a fair amount of time later. One of the reasons was this gentleman who was the first president of Caltech, actually, Robert A. Millikan, who, as a physicist, was mostly famous for his oil drop experiment that shows that electric charge is quantized. But he was very interested in these radiation problems at the time. And he eventually did his own experiments in the mid-1920s and became absolutely convinced that Mr. Hess was correct. He was so influential that at that point, people really started to believe that Victor Hess had demonstrated that this radiation had come from the sky. And Millikan, in fact, is the person who's credited with coming up with the term cosmic rays. He said these are indeed cosmic rays. So it's actually kind of interesting that there is a Caltech connection to all of this from the very early days. Now, there have also been important physics discoveries in cosmic rays, and so one always has to keep in mind that maybe this is an area where you can find some other new things. In fact, at Caltech in 1932, this gentleman, Carl Anderson, discovered antimatter, the antiparticles of electrons, using a cloud chamber with a magnetic field, as shown here. he then later, in fact, for that work, he shared the Nobel Prize with Victor Hess in 1936, it turns out. But he was still looking at cosmic rays in 1936 with his cloud chambers, and he found something called a heavy electron, which we now call the muon, which is just an electron, but it's 200 times heavier. And we now know there are other particles like this, and so it was the first inkling that there are generations of duplicate particles called families. And so this was also an incredibly important discovery. More recently, the first indications of neutrino mass in this huge, this is not my experiment, but there's another experiment in the same mine, Kamioka mine in Japan, called Super Kamiokande. The first evidence was found by this huge experiment for neutrino mass in 1998 from neutrinos that are produced by cosmic rays in the upper atmosphere. So there have been quite a few interesting discoveries, and one always has to keep in mind that there may be other things you can actually discover about physics by looking at cosmic rays. And so that's part of the reason why in 2002 we were delighted to see that Discover magazine published an issue with the cover saying an article, "The 11th Greatest Unanswered Questions of Physics." So for example, like number 9 is, what is gravity? But we were quite delighted to see question 5, where do ultra-high energy particles come from? And it's kind of a nice description that the reporters came up with. The most energetic particles strike us from space include neutrinos as well as gamma-ray photons, and various other bits of subatomic shrapnel are called cosmic rays. And they bombard the Earth all the time, and we'll talk about this as we go on. But you might wonder, how did Discover magazine come up with these questions? In fact, the questions came from a National Academy study. You can't tell this from the Discover magazine article, but the questions came from a National Academy study called Connecting Quarks with the Cosmos, 11 Science Questions for the New Century. And indeed, one of them was, how do cosmic accelerators work and what are they accelerating? A slightly more technical version of the question, but anyway, that's where all of that came from. And so it actually is, the point is that it actually is still quite an interesting question, as you'll see, of where do these high energy particles come from and how are they generated to have such amazing energies, and try to convince you that they really are extraordinary. So this is a graph of a compilation of experimental data, actually by a professor of University of Chicago, Professor Swarty. And you can see that this is the flux, or basically the intensity of cosmic rays. If you hold out your hand, how many go through your hand per second, for example, is related to this number. And down here is the energy. And this is what's known as a logarithmic scale. In fact, every one of these is a factor of 10 in energy. So this is 10 times more energy, this is 100 times more energy, 1,000 times, all the way up. So you can see there are many decades of energy on this scale. And these are actually, it's hard to see, but they're also logarithmic. And this is 10 to the minus 10, 10 to the minus. So these go in factors of 1,000, these numbers. So I like to, when I talk at like seminar day at Caltech and so forth, I like to mention that I'm probably the only person showing a graph with more decades than Gordon Moore, because he likes to show the graph of Moore's law showing the doubling of the number of transistors on computer chips every few years. And he has this nice logarithmic graph. Anyway, this shows you that the flux or the intensity of the cosmic rays as a function of the energy is falling very, very steeply. It goes pretty much like 1 over the energy to the power of 3. And there are a few sort of kinks in it, affectionately known as the knee or the ankle. But what I want to focus on is how small the fluxes of particles is. So at these most energetic ones, at these least energetic ones, you can see 1 particle every square meter per second. In fact, these generate the flux of particles at the surface of the Earth that really are about 200 per square meter at sea level per second. But if you go all the way down here to the knee, there's 1 particle per square meter per year. So that says if you build a 1 square meter detector, you have to wait a year to see 1. And then if you go down to the ankle, and this is the place where we're going to be really interested in these cosmic rays, you get 1 particle per square kilometer per year. So you would have to build a square kilometer detector and wait a year to see one particle. And then, of course, if you go way down here, the flux is down at 1 particle per square kilometer per century. So you need to build something that's many square kilometers. You can't build something that would fit on the site of JPL or Caltech, for example. You need something huge. And that's why people build these large detector arrays. Now, just to give you an idea of how high these energies are, it's hard to calibrate this with knowing that, that these are like a brick falling from a rooftop. But you may know that, for example, in Batavia, Illinois, there is what presently is the largest, highest energy accelerator laboratory in the world called Fermilab. And this is a picture of it, aerial view. And this laboratory can accelerate particles up to roughly this energy called TeV, 10 to the 12 electron volts. And actually, I've drawn this at 10 to the 13 eV, which is close to where the new particle accelerator that will supersede this one in Switzerland, beginning probably next year. So over decades, we've been able to build accelerators to measure particles and their properties in this energy range, all the way up to 10 to the 13. The cosmic ray spectrum, as measured, seems to go all the way out to 10 to the 20, which is more than 10 million times higher in energy than the highest energy particles we can make in the laboratory. So these are extraordinarily high energies, much higher than we have in the laboratory. Where do they come from? Well, there's a lot of evidence. People have studied these for a long time. The lower energy particles down here, which are more like 10 to the 9 or 10 to the 10, can be generated in energetic flares from stars and things like that. And so these are rather common. You see lots of them. The higher energy ones out at 10 to the 16 electron volts out near what's called the knee, there's fairly good evidence that they come from supernova explosions and that they're accelerated in the expanding shock wave around a supernova. And you can pretty much understand the flux of particles from this mechanism. As you go up in energy, though, the theoretical astrophysicists have fewer and fewer ideas, and it gets more and more difficult to generate particles of such extraordinary energies. So we have question marks. But one of the possibilities for what are known as ultra-high energy cosmic rays in this energy range of, say, 10 to the 18 to 10 to the 20 electron volts are what are called active galactic nuclei, which are very bright nuclei of galaxies that seem to have the capability of generating these jets of energetic particles. And they're the most likely candidates for these objects are supermassive black holes, maybe 100 million times the mass of our sun, that is accreting matter and acting like a huge, powerful dynamo, ejecting the matter into space, ionized matter into space. And it's thought that these objects might have enough power to make these really ultra-high energy cosmic rays. And we'll come back to this later in the talk. Now, for these cosmic rays, wherever they're generated, they have to get to us. We have to think a little bit about the properties of how they travel through space. And there are two really important aspects that I want to tell you about. One is the magnetic field. You may know that the galaxy and the solar system, so forth, there's a magnetic field everywhere that bends charged particles as they travel through space. One of the nice things about astronomy is that the light that you see is neutral. There's no electric charge in the particles of light, so they come straight to you and you can see the points of light in the sky where they come from, stars and galaxies. However, charged particles get bent by magnetic fields, which makes it very complicated to imagine how they might point back to where they came from. In addition, there's something called the Greisen-Zatzman-Kuzmin cutoff, GZK. We'll just call it GZK. And I'll tell you a little. This says that the high energy particles must stop. There's a place beyond which there should not be any more of these ultra high energy particles. And that's just about around 10 to the 20 electron volts. So what about the magnetic fields? So if you, these are computer simulations. particles with 10 to the 18 electron volts, 10 to the 19 electron volts, 10 to the 20 electron volts, propagating through the galaxy. So this is a chart that has kind of the size of the galaxy and a model of the magnetic field of the galaxy. If you study physics, you learn that the orbit, a radius of curvature of the orbit, how the particle bends, goes as the energy over the magnetic field. So as you raise the energy, the magnetic field is of course constant, as you raise the energy, the orbits of the particles straighten out because the radius of curvature is getting larger and larger and larger. At 10 to the 20 electron volts, they're almost straight. So you can imagine now that seems quite interesting. As you get to this 10 to the 20 electron volts, this is the only time where these particles will actually point back to where they came from. If you look at where one of these particles is coming from, you see it's all bent around by the magnetic field and it doesn't have any memory of where it actually originally came from. So you can't see points of point sources with this kind of a situation. So it's thought that with a little luck, if we can find particles at these very high energies, that they will actually point back to where they're coming from and tell us what are the objects that actually created them and accelerated them to these extremely high energies. Now the GZK cutoff is a little more complicated. Let's imagine that we have an AGN that has managed to power a 10 to the 20 electron volt proton, send it towards the Earth. Now between this AGN, which might be, I'm using the unit here, megaparsec, so it might be tens of megaparsecs. A megaparsec is 3 million light years. So this would be 30 million light years. And in between the AGN and us, there isn't a whole lot, but as you may know from studies of what's called the cosmic microwave background, there is a diffuse background of microwave energy. And people study that, and this is how we know that there's dark energy and dark matter in the universe. It's very interesting, and this shows a map from the famous COBE satellite that shows the fluctuations that indicate that those properties of the universe. But one thing we know from all of those experiments is that every cubic centimeter of space, we actually know very accurately that there's 411 of these cosmic ray photons in every cubic centimeter. And so we really know how many photons there are between there and there. And we also know that those photons will steal energy from the protons as they come towards us, creating other particles called pi mesons. We don't have to worry about what they are, but just conservation of energy tells you that these protons are losing energy. And this process turns off below about 5 times 10 to the 19. So once the protons lose energy down to about 5 times 10 to the 19 eV, then they're free to propagate through the microwaves. But if they have energy higher than that, they will lose energy due to interactions with the microwaves until they get down to this energy. And this was predicted right after the microwave background was first discovered in the 1960s. So people were quite certain that at around 5 times 10 to the 19, the cosmic ray spectrum should stop, assuming that they're protons and that they're generated at distances greater than 10 megaparsecs, for example. So there are a few assumptions, but this was the expectation. How do we detect such high energy particles? This is due to a famous French physicist named Pierre Auger, who discovered the property of cosmic ray particles known as air showers, which is due to their interaction in the atmosphere, and I'll cover that. But basically, he discovered in 1938 that over distances of 100 meters apart, you could see cosmic ray detectors fire at the same time, coincidence. And he hypothesized that this is due to the fact that the particles are creating secondary particles in the atmosphere, and so you can, and they spread out as they come down through the atmosphere, and you can see them simultaneously at different distances that's separated by, say, 100 meters. And this, in fact, turned out to be true. And this property of the, and this, as you can see in the background, I have this sketch of a single particle coming in, hitting a nucleus in the upper atmosphere, creating secondary particles. Those create lots of secondary particles. And then down at the surface of the Earth, you have lots of particles hitting the ground over a large area. And these air showers, the properties of these air showers can be used to study the properties of the original cosmic ray particles that cause them. So this is another sort of cartoon of this, where a single particle comes in, 10 kilometers high in the atmosphere, starts creating secondaries, and you get lots more secondaries. And then down on the ground, you can have a variety of methods for studying these air showers. If you go out where it's really dark in the desert, they do make some light called fluorescence light or scintillation light, and you can detect that with very sensitive photon detectors. You can also detect other kinds of light called Cherenkov light. We, in other experiments, use counters on the ground to study the particles as they hit the ground, separated over a large area. And just like when you want to know how many people attended the Rose Parade in Pasadena, you know, they don't have a turnstile and count every person that goes into Pasadena on New Year's Eve. They fly over in a helicopter and they pick out different little places. They sample, right? They measure, oh, they say there's, you know, a certain number of people and that's per square mile in this area, per square meter, and they just count, sample it. And then you say, well, then we can add them up that way. And we do the same thing. We just sample the air shower. It's too expensive to cover the whole ground. This air shower will be kilometers big on the ground. So we would need to cover an enormous area with detectors, and we don't have the resources to do that generally. This shows how the air shower develops in sort of an animation. And you can see that secondary particles are all created, and they come down in like a pancake because these energies are so high. All the particles travel at the same velocity, the speed of light. They're essentially at the speed of light. And it's slightly curved because, of course, as they spread out, some of the ones that are out in the periphery have to go a larger distance, and so they kind of fall behind, and you get this curved shape. But you can also see that they hit the detectors in sequence at different times when they come down to the ground, and that can tell you the angle at which the cosmic ray came from. This is a little better picture of it, showing this the particles in this sort of pancake-shaped thing, and there's a plane that you might, a tangent plane, and perpendicular to that tangent plane is the axis where the original particle must have come to create the shower of particles. And this comes down, and you'll notice it would hit this detector first, this detector second, that detector third. If the shower came straight down, then all the detectors would fire almost at the same time. So you can see the fact that they fire in sequence tells you the angle. And we can measure the timing that way and the direction. Now, I got interested in this subject back in 1998. There was an experiment in Japan that had about 100 detectors on the ground. And this shows a map of their detectors. And the size of these circles is how strong the signal was from an air shower in their detectors. And you can see it was a very well-developed pattern. At the center of the shower must have been here, and it spreads out over there. And this shows a profile as a function of distance from where the center is, that the intensity of particles falls off. So the overall intensity, as determined by an analysis like this, how high this curve is, tells you the total energy in the shower. And then the pattern in time of when the hits occurred tells you the angle and where the particle came from. In this way, you can measure the energy and the direction of origin of the original cosmic ray. So this Agasa experiment in Japan in 1998 reported this result. What they did was they measured the flux of cosmic rays, which, remember, was something that was falling like 1 over the energy cubed. To make it easy to look at, they multiplied by E cubed, so we should get something flat. And was expected that just below 10 to the 20, there would be this cutoff due to the GZK effect. And that's what this blue curve is. But they seemed to see a significant number of events beyond this, which generated a lot of interest. And people speculated that maybe these are leftover particles from the Big Bang decaying. There's all kinds of crazy, interesting ideas for what might have generated these particles, because really everyone believed in this GZK cutoff. So this became quite an interesting field in the late 1990s, and that's kind of when we got interested in it as well. Now, there's one of these fluorescence detectors in the desert in Utah called HiRes. They reported data recently. This is the same Japanese data shown here in blue this time. And the data from Utah shows this, which actually seems to look more like that dashed blue curve in the previous figure. And they seem to see very few events out here compared to the experiment in Japan. So there was a big controversy when I started getting interested in this subject, and it's really been quite fun to see what happens ever since. Now, there is a big new experiment. The really biggest new experiment is called the Pierre Auger project, named after Pierre Auger, who discovered air showers. And it's sited in Argentina in the southern hemisphere. And they are measuring a spectrum, and they reported this summer their energy spectrum. And I don't have it compared with the other data, but they seem to agree that the spectrum is dying very quickly around 10 to the 20 rather than continuing as the experiment from Japan would have said. So it looks like this Auger experiment is starting to agree with the Utah experiment, and that probably the GZK effect is really there. But they need to run longer and get more data to really be certain, but it's starting to look that way. And so this is the way Auger is done in Argentina, but many of these experiments have been done in the past, most of them smaller than that. And you can see that normally the idea is to go out to the desert somewhere where nobody will bother your experiment and you won't be in the way of anybody else. And you can see here's one in Utah where they put detectors all over the ground. This is the wing of an aircraft. They're looking down, so you can see. There's, let's see, here's New Mexico, something called Volcano Ranch, and this is one of the pioneers, John Lindsley, of this subject. And what he's doing here, that's his cosmic ray detector underneath a bunch of dead grass or something. And they had a lot of trouble with rattlesnakes, so when they were going out to see their detectors, he had to worry about whether there was rattlesnakes in there. This experiment had problems with, I believe it was field mice that they've populated these like a chain of hotels. They populated their detectors and became a problem for them. And this is the Auger project. They have much bigger detectors. These are about 3 meters in diameter, and they're water tanks, actually. And this shows a prototype, but they're out also in the desert in Argentina. And they all have this problem, as you might imagine, which is you've got to power all these detectors, you've got to get the data out of them, and all of that. And you could see the Auger experiment had these solar panels and everything. This is the kind of stuff that people at JPL are very good at, but putting a lot of, when you put something into space, you might have to worry about a cosmic ray hitting it once in a while. But when you put stuff out in the field, you got to worry about the animals and all this other stuff. So there's a lot of interesting features to doing an experiment this way. And of course, there's a certain amount of cost involved in citing experiments in these remote areas. So we decided that it would be interesting to try and build an experiment like that and try to study ultra-high energy cosmic rays in the Los Angeles area by putting the detectors in the high schools and middle schools and some elementary schools and some universities as well. And so we at Caltech, in collaboration with a professor at Cal State Northridge, Ryoichi Seki, and a professor in Irvine, Gorang Yod, who has been in cosmic ray physics for a long time, developed this concept of the CHICOS array, California High School Cosmic Ray Observatory. And the idea was to develop a distributed array of detectors to study ultra-high energy cosmic rays and then cite them in LA area schools. The advantages are sort of obvious. You get power. They presumably don't charge us for the power. You get a network connection because all the schools were just getting wired up to the internet, so we could get the data out fairly easily. There's shelter for your electronics in the building. You don't have to worry about the elements. And there's people to help you. They can help diagnose. They can reboot the computer or tell you what's wrong with it sometimes. And so there's people out where all of these detectors are and all the equipment is. So you can actually get them to help you diagnose problems. Since they're all operating independently, we have to know the timing very accurately of when they fire from the cosmic ray showers. And that's a new feature also. The global positioning system can tell us the time to a few billionths of a second, basically. And this is a new technology. Most people think of GPS as it tells you where you are. But the way GPS finds out where you are is it measures the timing relative to satellites distributed in the sky and then does triangulation, basically. And so it's fundamentally a timing system. So you can get timing very accurately from a GPS receiver, and they're very cheap now. So we could use commercial hardware for the computers and so forth. They don't have to be specialized things that you use almost no power, run off of a solar panel and so forth. They can be reliable and easy maintenance, easily repaired or replaced. And so this was the concept that we had in going about building this experiment. So this is what a typical setup looks like. There are 2 detectors on the roof of a school with a GPS antenna. The cables come down into the classroom, and I'll show you pictures. There's a little, basically a regular PC with a little electronics box and a monitor. And of course, then there's also a connection to the internet that's not shown here, where we can get the data sent to Caltech at night. It's a fairly simple concept. We just need to get the detectors on the roof, and I'll show you that we just generally take them up there with a crane. And most of the interaction with the school administration and so forth involves this part right here. You've got to get the cables from the roof into the classroom. So there's various little ways of making holes in the walls and in the roof and so forth. And this is where you obviously need the maintenance people at the school to help you out. So there's a little negotiation that goes on there. So we had to find some detectors. And I happen to know that there was an experiment called CHICOS in Los Alamos, New Mexico, up in the mountains. And you can see they had these detectors all over the mesa there. And just when I started thinking about this experiment, a friend of mine at the laboratory in Los Alamos called me and said, you know, I've got all of these were like 200 of these detectors. They're all out on the mesa. We finished our experiment. And the administrators here are really bugging me to get them off the mesa, because we can't just leave them out there forever. And I said, well, gee, maybe I can use them. And do you think I could have them if I came out and got them? And so he talked around, and they were very happy to have us go out there and collect them. And here you see a group of high school teachers and students from Caltech and visitors and so forth. We went out there on a trip for about 3 days and collected them all in a parking lot, and they then put them on moving vans like this. And you can see these kind of trees don't grow in Los Alamos, New Mexico. This is Pasadena, California, where we brought them here. And then we had to refurbish them and get them ready to go to the high schools in Los Angeles. Now, we didn't invent this, but the physicists that worked on the original experiment in Los Alamos liked to call those things schmooze. And that's based on something in the Al Cap comic strips from the 40s and 50s. And these schmooze were benevolent creatures that, and the physicists thought that their detectors looked like schmooze, so they called them schmooze. And I guess we still call them schmooze a lot of the time. So anyway, that's kind of amusing. But we had to get in the work in the lab and make these schmooze work. And so we had to re-outfit them with photomultiplier tubes, and we needed special high voltage supplies to power the photomultiplier tubes. Here's a little GPS receiver. These were brand new at the time. There weren't very many GPS receivers in cars in those days. This was, back in 2000. So these were new things. We had to learn how to use them. You can see the prototype electronics here and software. And it was great fun for the students and postdocs to work in the lab. And this is what we came up with. This is a PC, and there's a little electronics box. We need one little custom electronics box where all the cables come in, and then cables go into the back of the PC. And this is the circuit board. It's very simple. There were only 2 integrated circuits on it. And this is where the connections came into the computer. And so we designed the circuit board and tested it. And then we just needed to build one of these for every one of the sites. And so that's where some of our student help came in, as you'll see. And then we had software, and students and people working in our lab developed the software. It looks something like this. Every school has one in their, that's in CHICOS, has one of these computer displays in the classroom. And you can see this one says South Pasadena High School, and it shows the features of the data as it's coming in as a monitor. And so we can, by looking at this, tell how the site is working and how the equipment is working. Okay, so then we've got our equipment designed, ready to go. We've got to go put it out in the schools, and this is kind of what the situation typically looks like when we lift them onto the roof with a crane. It usually draws a pretty good crowd of students and so forth. Here's me standing next to. We typically separate them by 3 to 5 meters. And here's some Caltech personnel who normally they have rather uninteresting job of moving furniture around Caltech and things like that, but they really like this activity of going up on the roof and deploying these detectors. So it's been good fun. Each one weighs about 200 pounds, so it weighs it's a non-trivial weight, but it's not anything stressful really for the roof. And so here's a map of the yellow and orange are the sites that we have actually deployed. And in the San Fernando Valley, there are about 30 sites out there. And in the San Gabriel Valley, we've got 37 sites. And we've been taking data now for several years. The blue dots are sites that we just generated a catalog of all the possible sites just to see what you could possibly do in the LA area if you managed to put detectors in all of the schools. So you can see it would be a rather big array, not much smaller than the Pierre Auger Observatory in Argentina. So we're smaller than them, but we're actually, you can see, I think I have something, yeah. This shows you how big that original Agasa experiment was, which was the biggest experiment before 2000 when we started. But now there's the Pierre Auger experiment, which is probably as big as this whole picture. But we're a pretty good fraction of that, so we get some nice data. And they're in the southern hemisphere, and we're in the northern hemisphere. So it's not clear that we should see the same thing. Okay, and we've had lots of help from teachers. They help us put the equipment together when we show up. And even sometimes, this is a nice logbook. We have an electronic log, and this is one of our more not every teacher is this conscientious, but each day now the cosmic ray detector device shuts itself off. I believe it does so because it overloads its detected number of strikes, probably because of a light leak. These detectors have to be completely sealed against light because they have these very sensitive photomultiplier tube light detectors in them. I'm going to tape some tin foil over the sunny side of detector B, which maxes out, and see if that stops the morning light leak. And because you can see as a function of time of the day in the computer display if there's a light leak, because when the sun hits the detector. And so he kind of figured that out, and he said the A detector is 222, and B detector is 195. It looks like things are back to normal, back to physics lecture. So it's kind of, not all our teachers get to spend that much effort to help us, but it's kind of nice when they do. And then we have, instead of finding the electricity out in the desert, we have this new problem of, we need spare outlets for the electronics of the computer and so forth. All right, so teachers have also helped us by helping develop these teaching modules. We now have 15 activities which are available online. This shows one developed by Richard Buck, Louisville High School teacher, where he made a presentation at the National Science Teachers Association in March 2002. Showing how when a shower comes down, this is kind of a model for how a shower comes down, and measuring the time it hits two different places can tell you the angle. And so he had a nice little demonstration of that. This is our website, and you can see that there's different places you can click on for an overview, CHICOS for Students. And if you go to CHICOS for Students, you find that there's a whole bunch of stuff you can do. You can get information on what are cosmic rays for introduction to cosmic rays, and how does there's a balloon ride thing from the Utah experiment that we have a link to, and some various things about learning about cosmic rays. And then we have working with CHICOS data, so you can actually they can actually access the data and use them for projects. There's tutorials on the software, things about CHICOS in the news, and how to sign up for the summer research program, and maybe ask us questions and things like that. So the summer program is actually one of the more interesting and successful parts of this. Every summer, for typically a week, we have a group of students with a teacher. They come with a teacher so that we have someone who knows them already and so forth. And they come to our lab, and we get them doing all kinds of activities. I told you about those. We needed 67 of these little circuits, and you can see that we can train students to do building electronic circuits, something that I did when I was a kid a lot, but kids don't get to do very much these days. So it's really they love doing it. It was great experience. And then, of course, you build something and it doesn't work. You got to find out why. And this is all these things about building stuff like that people don't get that kind of experience very much these days anymore. And then here they actually helped us commission the detectors and got them working before we send them out to the high schools and so forth. So it's really, it's been and we vary it from year to year. People do different things from year to year. And here's another group. And so we typically run this for maybe 6, 7, 8 weeks in the summer. So we have maybe 8 groups come in each summer. And this has been going on now since, I think, 2002 or so. So we've had quite a few people come through this program. So what does the data from the experiment look like? Well, this shows you a graph of position. So this is east-west, and this is north-south position. And the units are kilometers, so there's 5 kilometers, 10 kilometers. And this is the area around Pasadena. Caltech is the center of our coordinate system, 0, 0, for obvious reasons. And so this is the Pasadena area where we have quite a few sites deployed. And this is the San Fernando Valley, where we have some that are more spread out, you can see. And this is one of our more spectacular events. You can see, I think it fired 16 sites in the area around Caltech, spread over, you can see, 10 by, this is as big as the whole Agasa array, like the whole thing fired at once. And then there's one site over here in the San Fernando Valley. Now, remember I told you that in a square meter you get 200 counts per second from cosmic rays, just random. They don't have, and so every one of our detectors is counting 200 times a second, and each of those counts doesn't have anything to do with another count. They all come from very low energy events. But so you can see that it's not too unlikely that there would be randomly by accident a hit in some detector somewhere. And typically, on the average, there's 1 or 2 of these so-called accidental fires of detectors. And so we know that this is most likely an accidental event and would not belong to this shower. The other thing about these events is that there's the color coding. We also have the size. It doesn't work too well, but the size of the circle is proportional to how strong the intensity of the shower was at the location. But the timing is indicated by this color coding. And I actually forget now whether it starts with the red and works its way over to blue or the other way around. But it tells you, you can then see which way the shower was tilted as it came and hit the ground there. And this is the same event blown up so you can see it. All right, and so here Caltech is at 0, 0 right there. And so you can see the detectors that were hit all over here. And you can see it was a progression as we go down here. And here's our software, gives us a result for the direction with fairly good accuracy for such a big shower like this. And an energy that's pretty close to 10 to the 20, a little less than 10 to the 20, 9.16 times 10 to the 19. And so this is actually a very good, well-characterized event for us. And we like that. When you go out to the San Fernando Valley, where our detectors are further spread further apart, you can see that we get fewer hits, but it's really unusual to see hits fired over such a large distance. And so we know that this is a real event, and we can analyze this as well. The data are less precise because there are fewer sites hit, but you can see that this one actually says 1.37 times 10 to the 20. So this is one of our highest energy events that we've seen, by the way. So, but there is an uncertainty in it. This is in a log scale. So 10 to the 20, the log 10 of 10 to the 20 is 20. So this comes out to be 20.14, and the uncertainty, according to the software, is 0.173. So it actually might be slightly less than 10 to the 20, but this is the most likely value based on this analysis. Now, this kind of gives you, the triangles show you where the detector sites are, where the schools are that we have detectors, and these red dots are the positions of all the data points that we have. All the events that we've detected over the last few years are shown on this graph. I think there's 280 or so of them, and you can see the dots all over here. And there's a higher density of them in the Caltech area in the San Gabriel Valley because the sites are closer together, and we can see lower energy cosmic rays. And since the spectrum is falling like 1 over EQ, there's a lot more lower energy events. So we picked those up here. And only the really highest energy events can be seen using detectors that are spread further apart, as they are in the San Fernando Valley. And this you can see in this type of a plot where we put a cut on the energy. We take only the energy of events where the log of the energy is greater than 18.8. And you can see then it's a little more uniformly spread out. And this is more intense, but not like it was before. But if we take only the lower half of our events, the lower energy half of our events, all of them are where the detectors are close together, and none of them are out here. And so this is, we don't have a spectrum to show you that it goes like 1 over e cubed yet. We're still working on that. But this shows you there are actually 272 events in our sample and shows you what the distribution looks like. And you can see there are a handful of events up above 10 to the 20. And so we've actually got some interesting things to look for. And of course, we want to try and generate a spectrum on this. And my graduate student is working on that at the moment. But there's something else we can do that I want to tell you about. So just last month, the Pierre Auger project in Argentina reported a result where these red X's are a catalog of nearby active galactic nuclei, the things that the theorists think might be the most powerful engines for generating these ultra-high energy cosmic rays. And these circles are where their most highest energy events are. And it's a little hard to tell, but you can see that there's more, there's kind of a cluster. These are in galactic coordinates, and this is something called the plane, the supergalactic plane, which is the plane for the local cluster of galaxies. And you can see there's a clustering of the AGNs, active galactic nuclei, along there, and you can see the highest energy cosmic rays where the circles are also are along there. And this white dot has 2 circles around it. And the white dot is that Centaurus A active galactic nucleus I showed you that picture of, the X-ray picture of at the beginning of the talk. It looks like that is indeed a source of ultra-high energy cosmic rays. So this is quite exciting and is a new thing that this Pierre Auger collaboration has just put out. And obviously, we can do something they can't. We can take our highest energy events, which you see we have a bunch of, and we can search the northern hemisphere and see if there's a correlation with the AGN catalog for the northern hemisphere. So we'll be hopefully doing that in the near future as well. So to close, I'd like to acknowledge the help of everyone that's been involved with this project. This is kind of a slide that shows some people who have been involved on the Caltech side, who've been working with our team at Caltech. Many have moved on to other positions. This was Michelle Larson, our first coordinator. She's now like a vice provost at some university in Utah. Can't remember which one. And this is Teresa Lin, our more recent coordinator, who's now an assistant professor at Harvey Mudd College. It's my graduate student, Alina. And Bob Gates, who's here, who is a retired high school teacher from Birmingham High School, who has helped us with the summer program and various other parts of this project for years now. He's been a great help. And here are the names of various people that have helped us, and some of them have moved on, some are still with us in the lab. But it's there's been quite a few people come through our lab, and this doesn't even list all the students, undergraduate students, students from other community colleges that have come and helped us during the summer and so forth. And of course, lots of teachers and students who have come to the summer programs and workshops that we hold on Saturdays. And these are just a few of the pictures. There's just, there's been basically hundreds of students and teachers that have been involved with this project, and I think has benefited many of them a great deal. So I think it's been a very successful project. It was kind of risky, wasn't sure how we were going to do this at the beginning, but I think we've managed to successfully combine research and education and outreach in this project. I've met lots of teachers and students that I never would have met before, and they've been exposed to things that they would never have been exposed before to. As I said, there have been hundreds of teachers and students. We'll be coming out with hopefully more science results soon. You can see we actually do have some data to analyze. And I'd like to thank the sponsors. You can't do, even though this project is kind of done on the cheap, can't do anything without some funding. And so we've gotten we've got the detectors from Los Alamos. IBM has donated computers. Weingart Foundation has given us some funds. Caltech gave us some seed funding, and also the National Science Foundation actually continues to fund operating the experiment. So I thank you for your attention, and I hope to come back and tell you about some exciting results sometime in the future. I assume we have questions if people.
Yeah.
Okay.
We'll take some time. Any questions for Dr. McKeown?
Sure. I was wondering if you can look at the possible identification with a particular source. I'm thinking a good one in the northern hemisphere might be Perseus A or something like that way out there. And if you get an identification with something like 350 million light years away, and you know how much energy these things lose along the way, did that give you an idea of, my goodness, this thing to get to the Earth might have had an original energy of 10 to the 23rd or 10 to the... Does this give you a cutoff on the top energy?
Well, that's an interesting question because you would need to get quite a bit more data than we anticipate that we could get now. But indeed, if you got lots of data from these AGNs, for example, and could look at if you could get the energy spectrum for each one and look at the difference for different distances, you would be able to see this GZK cutoff develop, for example, and be able to say more about what the original spectrum was before the GZK effect distorted the spectrum. So that, but I think maybe Pierre Auger, if they talk about running those experiments for a couple of decades or maybe 30 years, so they will get a lot of data. I don't know if we can keep our experiment going that long, but they will get really a lot of data, and they might be able to say something along those lines. It's a very good point.
My question is, would neutrinos be expected to follow the same drop, like the same cutoff?
Very good, very good. So, when the protons lose energy and make these pi mesons, I wrote down the neutral pi zero, but there's also positive pi pluses, and they decay and make neutrinos. So, as the protons lose energy due to the GZK effect traveling through the microwave background, they actually will be generating neutrinos. And there are experiments being designed right now. They generally go down to the South Pole, which is, you think Argentina is a harsh environment. The South Pole is very difficult. But they're very exciting experiments to look for high-energy neutrinos that would actually be generated by this GZK effect. So actually, these cosmic rays should generate neutrinos that can be detected. And that would be another important clue about the original spectrum of the protons before they lost their energy, for example. Yes?
Yeah, any idea of the actual mechanism of what possibly produces them? I mean, is it a accretion disk around a black hole, magnetic fields? What would produce these super high energy cosmic rays?
Well, normally the way you think of this is there's maybe a rotating magnetic field. So there's a time-dependent magnetic field, and if you remember Faraday's law, time-dependent magnetic fields give you electric potentials, which can accelerate particles. It's kind of a naive way to think of it, but in general terms, it's not unreasonable. And so you have these rotating objects. They can act like big batteries and accelerate particles. And that's one idea for how these things... The supernova is a rather different mechanism because there you have this expanding shock wave, and particles rattle around in the shock wave and fall out, but they get accelerated on the average as they rattle around in the shock wave. And so that's a rather different mechanism. Whether there's a shock wave involved with these other processes is hard to tell. It seems like it's probably something else. But
Merging, colliding with stars, things like that.
There are lots of speculations. It's actually difficult. I think it's to actually do a fair calculation that gives particles at these high energies is difficult to do. It tends to be rather speculative. So it's very exciting if what the Auger project is seeing, that there actually are these AGNs are actual point sources. It's a major clue, and I think the theoretical astrophysicists will focus in on that and try to learn more about what the mechanism is and how it actually works. And if we can measure how many, if we can determine that the flux of cosmic rays is different from different AGNs, for example, we can really learn a lot, things like that. So it's a fairly speculative subject right now. These guys came armed. That's great. Go ahead. Go ahead. That's wonderful.
Question about the original particle and the detected particle. Do you think there are as many electrons as protons? Clearly, they would have less energy or lose it quicker. But I mean, do you think that the primary cosmic rays include, more than just protons?
The electrons do not propagate as far as the protons. So,
By the magnetic field.
yeah.
And are you actually detecting secondary? Are they muons, or what are you actually detecting? In the shower, all of those particles in the pancake, the dominant component are electrons and positrons. Okay, there are a few muons. About maybe it's down by about a factor of 10% or so are muons. Okay, but if you look at the individual, when the detector is firing 200 times per second for a square meter detector, those are mostly muons. Because for the low energy, for the very low energy cosmic rays, they generate just small showers that peter out in the upper atmosphere. But muons are very penetrating particles. They always come down. So if you look at single particles, there's a lot of these muons. But in the showers, it's a lot of electrons and positrons. It just turns out you just generate a lot of what's called electromagnetic energy, because it's easy to make photons that then convert into electrons and positrons. And they multiply and multiply and multiply because they're light particles. They're not heavy. Yes?
You were saying that you were detecting neutrinos. I thought they were very difficult to detect. And how do you do that at the South Pole? I mean, they take this huge thing in Japan to do it.
Yes. Well, at the South Pole, they have some. All right. So the experiment in Japan was water, it must be something like 20 or 30 meters on a side, the water. So I know the mass is 30 kilotons, but I can't remember the exact size. It must be like 30 meters on a side. So it's just a big vat of water, and it has photomultiplier tubes looking at the water. When the neutrino interacts in the water, it creates an energetic particle. And that energetic particle emits light called Cherenkov light in a cone along the direction of motion. And they can see that with these photomultiplier tubes, and they can tell where the neutrino came from and so forth. And that's how they detect the neutrinos. And so if you accept that, then you see they go to the South Pole, and the plan is to use the ice. Okay? The ice is already there, obviously. And so, well, it'll be there long enough to detect neutrinos, I think. And so what they do is then they use water and drill a hole in the ice, and they lower down a string of these photomultiplier tubes into the ice, fill it with water, and let it freeze over. And then they've got the photomultiplier, and this is called Ice Cube, is the detector. It's funded by the National Science Foundation. It's still under construction. They haven't finished it. But it is, it's like a kilometer cube. So instead of being 30 meters by 30 meters by 30 meters, it's 1,000 meters by 1,000 meters by 1,000 meters. So it's much bigger and would be much more sensitive to neutrinos. Now, they will also see lots of cosmic rays coming from above. But the trick they use is they look at particles coming up from the center of the Earth. So the Earth absorbs all the regular cosmic rays, but neutrinos come right through the Earth. And when they come right through the Earth, they will interact in the ice cube detector and make upward-going muons that are a signature of detecting neutrinos. Yes?
What is the speed of the high-energy particles?
They are essentially the speed of light to very high. Very close to they can't be greater than, but they're a very tiny amount less than the speed of light. So they basically are all going at the speed of light. Technically, if you know some relativity, the idea is that the energy, when the energy is much larger than the mass of the particle, then it's going at the speed of light. So for a proton, its mass is 10 to the 9 electron volts. So once the energy is much bigger than 10 to the 9 electron volts, and we're talking about 10 to the 19, 10 to the 20, so it's very high, then the particle is going at the speed of light.
At that velocity, how is it possible to really detect a time difference between arrival of one detector and another?
Oh, sure. Well, you can tell by if you just do the simple trigonometry. You know, particles at the core of the shower have to go maybe an extra few kilometers than the ones on the edge that hit the detectors first. Okay, and the speed of light is 3 10 to the 5th kilometers per second. So a few kilometers is going to be 10 microseconds or something. And the GPS accuracy is about 50 nanoseconds, 50 billionths of a second. And so we're looking for time differences that are several microseconds, several millionths of a second. So it's actually quite easy to measure that amount of time.
I guess well, the question was is that so protons primarily lose their energy at that level through photopion production.
Right.
Is it known how neutrinos, if the neutrino has, let's say, an energy of 10 to the 20 eV, what its primary energy loss mechanism would be with the CMB?
The CMB would be very transparent to neutrinos. Neutrinos is why one of the reasons people are so interested in neutrinos is not only don't they bend because they're neutral through magnetic fields, they don't get absorbed by anything. So they'll come through anything and point back to where they came from. So if we can really detect, this is why this ice cube experiment is really quite important. If we can detect neutrinos coming from point sources in the sky, that would be very exciting and give us a lot of information about high energy astrophysics. They're like the best particle. They're hard to detect, but if you can see them, they will be the best high energy particles because they will definitely tell us where they came from.
Was there any work done in the lab? Freezing these photomultiplier tubes, it kind of bothers me. So I'm wondering if there is anything discovered about that when people were testing that, if that's going to work.
Oh, they tested it very thoroughly, I assure you, because they have to put hundreds of them in the ice. They're contained inside a sphere, which I believe is an acrylic sphere. It's a transparent. I know everything, the photomultiplier tube and the electronics is all in a sphere, and they have these spheres on cables and lower them down into the ice. And they have, I'm sure they have a good website with lots of pictures of this, but they've tested this very, very thoroughly, actually, I'm quite sure, so it's not a problem. And once they're in the ice and frozen, I think they're quite safe. You may know the Superkan-Miyokande experiment, the Japanese experiment I told you about, they had 11,000 of these photomultiplier tubes, and they're really big ones like this. Each one cost $3,000, so you can imagine how much money this is. And they had an accident where one of them broke. Now, one of them breaking out of 11,000 is not a killer, but it created a shock wave in the water, and that shock wave broke all the other ones. They were doing maintenance at the time, so the detector was only half full. And so they broke 6,000 of these very expensive photomultiplier tubes. So you do have to worry about these things. But I think the ice cube people have been very careful about how they deploy those photomultiplier tubes. And they shouldn't have shock waves anyway, not like the...
I know we're just getting started with this exciting science, but at this point, does this, or can you see this, putting some kind of constraint on some of the exotic dark matter candidate particles that we think are axons or something like that?
Like I say, there was lots of speculation that the really highest energy cosmic rays may come from heavy dark matter particles that are relics of the Big Bang. People have incredible imaginations, and they publish papers with all kinds of ideas, and you never know which one may be right sometimes. So people write everything down, even though it sounds a little crazy, so there's a lot of ideas. I think when this Japanese experiment, the Gasa experiment, first came out and said there's excess of particles at the extremely highest energies, many people felt this is a clue that something, and there were lots of ideas like that on how to generate these really high energy particles and avoid this GZK problem and all of that. I think now that the data are settling down to look more like the GZK effect is there, this is all becoming a little less fashionable. But the dark matter is still very mysterious. Dark matter and dark energy are still very mysterious. There are many experiments being mounted now to study these things. We've only known about them now for a few years. This is very new, dark matter and dark energy. So there's a tremendous amount of interest in finding out what this is. People, I read recently someone said it's like Copernicus all over again. Copernicus figured out the Earth wasn't the center of the solar system. It's like a revolution. Now we're finding out that the matter that we're made of is only a small fraction of the matter in the universe. We're much less significant than we thought we were. So there's a lot of interest in what is all of that stuff and what does it mean for the evolution of the universe and how we understand, that the universe is made.
Okay, well, let's thank Dr. McKeown for a riveting talk. All right, thanks a lot.
Okay, thank you.
And thanks for coming. And please do remember next month, join us down at the Caltech campus for the premiere of Blaine Baggett's video. Good night.
Because I hear myself. How are we doing on NASA? Oh, I see. Who is that in the picture?
That's Don Yeomans at the...
Hello, Don. John Coleman in San Diego. How you doing?
I'm doing fine, John.
Did you stay up late last night drinking champagne and
I
acting silly?
somehow missed the champagne, but I did stay up last night.
We'll be ready to go.